Welcome to this colloquium talk. Today we are honored to have Professor Shu Gao of Nankai University to give us a colloquium lecture. His title, as you can see, is Descriptive Set Theory as a Complexity Theory, which is very exciting, and there are many deep results to classify many mathematical theorems, particularly analysis, functional analysis, dynamical system, etc., etc. And it's a very rich and developing area. So now let us welcome Professor Shu Gao to give us the full story. Thank you.
Okay. Thank you very much for the invitation. It's great, always good to come back to BIMSA. I've been here a couple of times, but every time it's very exciting and very nice. So thank you for being here today. And so today I'd like to talk about my research area, but I want to give a very general talk. So I wanted to say there's no proof, but there is one proof. But other than very short proof, everything is very high level. I want to just explain like what we do and why we do it. Okay. So this topic over here, I will say what descriptive set theory is about, but why do we consider it as a complexity theory? Is because we want to measure the complexity of various different mathematical problems and objects. And I want to, before I start, I want to say that the general complexity theory, in any complexity theory, there are like two types of complexity theory. One type is you set up some absolute benchmark, and then you actually compare, like, then when you have a problem, you say, which level is this on? So in general, there's some hierarchy going on, and then every time you have a problem, you try to identify the level of the hierarchy this problem is in. So that we call this type of thing the absolute complexity theory. And then there's a relative complexity theory, which is we don't have a kind of a general sense of hierarchy, but we have the general method is given two problems, we try to compare whether one problem is more complex than the other. Okay, sometimes we can do that, sometimes we can't, but when we can do it, this establishes the sense of relative complexity between the two problems. So we call this a relative complexity theory. So here I'm going to talk about descriptive set theory as both an absolute complexity theory and the relative complexity theory. But I will focus on the relative complexity theory part. So the first, I want to, the outline of this talk is there are four parts. So once we talk about, establish this general sense of the complexity, we will talk about how to apply this theory to the study of classification problems in mathematics and try to understand the complexity of these problems. Okay, so first let's talk about the absolute complexity theory. The sense, so I talked about the hierarchy, and the one of the hierarchies that we use is the Borel hierarchy. So let me just go to this kind of general framework. In general, we study a topological space, a type of topological space which is called Polish. And these are separable and completely metrizable spaces. So why these spaces? Well, the real thing is that we want to study, at the beginning, we just study the reals, okay? So the space of reals, which is actually a canonical space, but then we found that this theory can actually be generalized to this more general kind of topological spaces. And there is a good sense that these Polish spaces actually are very, very close to the reals. So if you think about, if you're not familiar with this notion of Polish space, just think about the reals, okay? So then the Borel hierarchy on the Polish space is defined as follows. First, there's the open set, because we have a topology, so we have the open sets, and then we have the closed sets. These are the simplest first levels, okay? Obviously, the closed sets are actually the complements of the open sets, so we view this, and we view that the collection of closed sets to be obtained via this kind of operator of taking, I put a negation over here, to represent the complementation of this class of sets, okay? And then the next level is what's known as F sigma, but we, in discrete set theory or in logic, we give it a fancy kind of notation called sigma 02, which is sigma 02 sets are exactly the F sigma sets, which are the countable unions of closed sets, okay? And we also view this as a type of operation, which is basically you take the collection of closed sets, and we use this existence zero, sub zero, as to represent the operator of taking the countable unions of sets in there. You get a new collection. This is the sigma 02. And then from that point on, you use this, you take the complementation again, which is called pi 02 or G delta sets, and et cetera, et cetera. So this can be repeated in general. So in general, we can talk about for an ordinal, countable ordinal, that is, between 1 and what's called this omega 1. For a countable ordinal alpha, sigma 0 alpha is just obtained by starting from all of the classes, pi 0 beta classes, and really take the union of all of them, and then apply this countable union operator to it. Okay, you get this, and the pi 0 alpha is then the complementation of the sets in sigma 0 alpha. So if you do this, the entire, the collection over here, we have put the Borel sets into hierarchy, like there are omega 1 many levels over there. So if this set belongs to any of these levels, we call it the Borel set. Of course, everybody is already familiar with the notion of Borel sets, which is the usual way is defined. It is that it's the smallest sigma algebra generated by all the open sets on the space, right? So, but this, what I just articulated in the previous slide was a way to actually carefully divide the Borel sets into omega 1 many levels. And we know that every level, there are some new sets showing up, okay? So this will already provide a sense of complexity for sets, okay? Like if your set is on the 5th level, not on the 4th level, that means that it is more complex than the ones on the lower levels, okay? Well, that's sets, but then after that, we can actually also talk about the maps. Like if you have two polar spaces and there's a map between them, okay, everybody's familiar with this. You say that a map is continuous if the pullback of all open sets of the target space, every one of them is an open set, the pullback is open, okay? So in our fancy notation, we can say that the pullback of the collection of the sigma 01 sets on the target space are contained in the sigma 01 sets of the source space, okay? And then we can define the notion of Borel map, which is in the same spirit. We can say that the pullback of open sets, if it's a Borel set, then we say that this map is Borel. Okay, and also there's this with this you can establish a sense of Borel isomorphism, which is if you have a Borel bijection between the two spaces. Usually when we say isomorphism, we mean a bijection, and then it is kind of, when we say homomorphism, you say continuous one way and then continuous the other way too. Here, we just said one way. It's Borel one way. What about the inverse? Well, there's a fancy theorem proved by Luzin and Suslin about a century ago, which says that if you have a Borel map, which is a bijection, then its inverse is automatically Borel. Okay, so and the important fact which will explain why we study polar space is that in fact any uncountable polar space is Borel isomorphic to R, to just the reals. So essentially we're just studying the reals. Okay, except that we can set it up in a different but by going to this polar space, we are able to study more kind of other spaces which appear more complex. Okay, all right. This is like and also any countable infinite. I just want to mention there are only two types of essentially only two types of infinite polar space. One is countable infinite, and the other one is uncountable. And the countable one is roughly Borel isomorphic to the natural numbers, and the uncountable ones is just the Borel isomorphic to the real. Okay. And then from this point on, you can actually this is the Borel hierarchy, but you can go further. So in descriptive set theory, we also study the so-called projective hierarchy, which is a higher hierarchy. And but I'm going to just go a little bit toward that direction and stop at the notion of analytic. So a subset of a polar space is analytic, or this time we use the fancy notation sigma 1, if it is the continuous or Borel image of another polar space. Okay. Here, whether it's continuous or Borel doesn't make any difference. Okay. It ends up being the same notion. Okay. And then, in the same spirit, we could actually consider the complementations of the analytic sets, which is called, this class is called co-analytic. Okay. And then in general, you can go up, but I'm going to stop here because, well, I hope it's not offensive to Hugh, because Hugh studies the entire projective hierarchy and further, but for most of the problems that we study, we stop at the analytic, because the majority of the problems that we study that come from the natural mathematics, they are already in this class of analytic or co-analytic problems. Okay, so anyway, I just want to mention that the notion of analytic and co-analytic has a nice connection with the Borel sets. Well, via this great theorem of Suslin. But Suslin said that this theorem is that a set is Borel if and only if it is both analytic and co-analytic. Okay. Great theorem, and because of this, we also we really do that. We also denote this collection of all Borel sets by this delta 1. This is our fancy way of denoting Borel sets, the collection of Borel sets in logic. That's a quick kind of introduction of the so-called absolute complexity theory, because, well, it looks rather trivial, but a lot of problems like proving something belongs to a certain level of the Borel hierarchy, or proving something is Borel or not, sometimes is highly non-trivial. Okay, to give you an example, like. About 15 years ago, someone published a paper in the Annals of Mathematics proving just one theorem, that a certain relation is non-Borel. That's all the paper is about. Okay, so but I will probably get to it at the end of the talk. So, well, with the absolute complexity theory, sort of the framework, I just already talked about it, and here I'm going to move on to the relative complexity theory. So the relative complexity theory, it turns out that the most successful one is this theory about the complexity of equivalence relations, rather than complexity about just the sets. Okay, so I'll just say why that's the case. But let's let's just take a look at this formal definition over here. Is like if you have two equivalence relations on two polar spaces respectively, and we can try to compare the relative complexity of these two and say maybe one is more complex than the other. Okay, so this notion is Borel reducibility notion. So an equivalence relation E is Borel reducible to equivalence relation F if there is a Borel function that basically translates problems about E to problems about F, and then get the answers that way, which is to say that you have this theta, so that if you have two instances x and x prime, and you ask whether they are E equivalent, all you need to do is to compute the theta values of x and x prime, and get an answer whether they are equivalent under F. Okay, so the question about E is answerable via this reduction as well as an understanding of F. So this is a indication that the information of F, I mean, there is more, the information about E is already coded in the information about F. Okay, so this is a relative complexity notion, very simple one. And we could actually go further and say that if E is reducible to F and F is reducible back to E, then we can consider the E and F to be of the same complexity. So then we say that they are Borel bireducible. Okay, and then there's also the notion of strictly Borel reducible, which is E is reducible to F, but F is not reducible back to E. Okay, so this is just a sort of a pre-order over here that establishes a sense of complexity between equivalence relations. Okay, and just this very simple notation, this very simple notion over here is the start of a very pretty theory of complexity for classification problems in mathematics. So we'll see. So let me just give you a whole bunch of examples of equivalence relations that are considered in this theory over here. Of course, the simplest one, here are simplest ones, the equality on a Polish space. Okay, so there's the equality on the natural numbers and equality on the reals, and it's not surprising that the latter one is more complex, strictly more complex than the previous one. Okay, and because the space of reals is actually Borel isomorphic to any uncountable Polish space, it's not surprising that their equality relations are happening on the same level. So they're compared at the same level of complexity. But then the first non-trivial example I want to talk about is this equivalence relation. We denote it as R mod Q, which is you can view it as just the coset equivalence between points of reals with respect to this subgroup R, additive subgroup of rational numbers. So in other words, two reals are equivalent if their difference is a rational number. Okay, so we call this the Vitali equivalence for the obvious reason that Vitali actually considered this equivalence relation, and what he did was he considered this equivalence relation between 0 and 1, and then he picked a single element from each equivalence class and formed this set, which is called the Vitali set. And he proved that this Vitali set can never be Lebesgue measurable, right? And for the same reason, we will see that gives also a similar reason to give that this Vitali equivalence is strictly more complex than the equality on the reals. Okay. The proof method is sort of the same. Okay. I want to move on to talk about these other equivalence relation, like this called the E0 in the theory. This E0 equivalence is defined on the space of infinite sequences of zeros and ones, okay? And the infinite sequence of zeros and ones, known as the Cantor space, is a polar space, right? Because it's a compact, metrizable space. And so if you have two infinite sequences of zeros and ones, they, x and y, they are E0 equivalent if they are just eventually agreeing with each other. So in other words, this is saying that there is a point, capital N, so that after that, the x and the y just agrees, okay? And one can easily check that this is an equivalence relation, and it is a fact that it turns out that this Vitali equivalence is actually bireducible with E0, so they actually happen on the same level. You can, if you just wonder about the complexity you can talk about either of them, and both of them are strictly more complex than the equality of the reals. Okay, so this gives a sort of the first interesting example of equivalence relations, and to be compared to. Like next time you have a kind of an equivalence relation, and you don't have to. You can compare it with the equality on reals, but then after that you can also compare it with the Vitali equivalence and see what happens. Okay, so in general, there are where do the equivalence relations that we study come from? Well, it comes from group actions. So I want to just tell you that story over here. So first, the groups, okay, we use are also Polish groups. So a topological group is Polish if it's just a underlying topology is Polish, okay, it's a topological group. So there are many such examples, additive groups of R and multiplicative group of positive reals, and all of these separable Banach spaces. I emphasize separable because I want them to be Polish, and for example C0 and LP, these are examples of Polish groups. Of course, they are Banach spaces, but they are also Polish groups at the same time. And for example, the unitary group is a very familiar object in mathematics. And other than that, we have all sorts of other objects. For example, all countable groups with discrete topology can be viewed as Polish groups. And a particular one that we will talk more later is the permutation group of a countable infinite set. Okay, we call it S infinity, but other people might call it the SIM-N or symmetric group of natural numbers or something like that. Okay. With the pointwise convergence topology, this becomes a Polish group, and there are many more examples. Okay, so once you have Polish groups, and oh yeah, I don't want to. This is a digress, a little bit digression over here, which is what are some other examples of Polish groups? Because we're going to use this example later. Well, let's consider some separable complete metric space. We call it the Polish metric space because they're separable complete metric XD. And if you consider the isometry, all the isometries of such a space, they make a group, right? All of these isometries under composition. Okay. Then equip it with the pointwise convergence topology. This is always a Polish group. Okay. So this will give us not just one example of Polish, but a whole bunch of examples of Polish groups. And I wanted to mention that in 1927, this is almost 100 years ago, right? In fact, Wurzon's result was proven in 1925, so it was over 100 years ago, that there is a universal Polish metric space. Like, it's called universal because it is such a big space that it contains a copy of every other Polish space, metric space. Okay, okay, and Wurzon's result, it has an interesting story I want to maybe share over here. Of course, if you know a little bit of history, Wurzon already died in 1925. This paper of 1927 that was published, it was written by his friend Alexandrov entirely, every word of it. But Alexandrov signed the name Eurozone because he basically said that this is Eurozone's last piece of research work before he died, and he drowned, right? Eurozone when he was 24, I think. So, but this is why, like, we refer to it as 1927, even after his death, because the paper was published in 1927. Eurozone's result was actually forgotten for over 50 years, and then some Russian mathematicians rediscovered it in the 80s, and in 1990, Uspansky proved that if you consider the isometry group of the Eurozone space, which is a Polish space, which we just mentioned, okay, this happens to be a universal Polish group, it is a Polish group. Not only that, but it's also the biggest one. Like every other Polish group has a copy in there, okay? It is a closed subgroup of the isometry of U. And then just out of curiosity, I want to mention that a joint result with Aleko Kekris in 2003 is that we actually proved that, in fact, all Polish groups arise this way, okay? So if somebody give you a Polish group, you can find a Polish metric space so that the isometry group of this Polish metric space is exactly the Polish group that you got, okay? So in other words, this is not just the one class of examples, but it's all examples of a Polish group, okay? Anyway, we'll actually use this Eurozone space later, okay? And now we have groups, then we consider group actions, okay? If you have a Polish group, okay, sorry. Yeah, I shouldn't have pressed this too hard. Okay, sorry, thanks. If you have a Polish group and the Polish space and the group acting on the space in a Barral way, okay? This Barral action over years, because the action is just officially a map from G cross X to X. Both these will be, on the left-hand side and on the right-hand side, will both be polar spaces. And so it makes sense to talk about the Barral maps, okay? So if this action is Barral, then we consider the orbital constellation, which is basically that the two elements are equivalent if they're in the same orbit, okay? There is a group element that transfer one element to the other, okay? So many examples of equivalence relations that we mentioned are already orbital constellations. For example, the identity is just a trivial group action. And if you think about it, the Vitali constellation is an orbital constellation because the acting group is the rationals with the discrete topology, okay? So, and then with that, you can actually go further. You can just consider, for example, infinite products of this thing, which is happening in R to the n, and you use Q to the n as this infinite product as the additive group over there. So this will give you more complex equivalence relations. And I also mentioned that all of those C0, the Banach space C0, LP, etc., they are Polish groups, so we can try to actually use them to generate equivalence relations such as, what we call C0 equivalence relation and our LP equivalence relation. Okay, and here I shouldn't have said P equal to infinity because L infinity is not a Polish group because it's not separable. Okay, but it does make sense to talk about this equivalence relation. Okay, and except that it's not officially an orbital constellation. Okay, as there are many more examples. So let me just give you a quick summary of how, some of these equivalence relations compare to each other in the sense of broad reducibility. Okay. We mentioned just now that the equality relations are very, they are actually simple, and compared to the R to the Q is actually more complex than them. And then there's the LPs, including the L infinity, but L infinity I use a slightly, a different font over here to indicate that it's not really there, but it can be there, and as an orbital constellation. And then we have this infinite product, C0, etc. Okay. So then here in the central line, I have some others like E infinity, equality plus, etc. So let me explain what they are because they will show up a bit later. Okay. So you can see that the point I want to make is that just these equivalence relations, they are already kind of painting a rather complex picture. And it's the collective work of many researchers since the 90s that we got this type of picture. Of course, we know more because some of these, there are small words in between. For example, there's a small word in between this Vitali equivalence relation and E infinity. So there are many, many things in between over here. But others, we sort of know that there's nothing in between. For example, this product over here and the Vitali equivalence relation, and between this Vitali and its product, there's nothing in between. Okay, so we know something, and then we know there are also open problems. For example, one of the open problems is we don't know if there's anything strictly in between small L1 and the Vitali. That's still an open problem. Okay. So anyway, let me define this E infinity because I want to talk about it later, and also this equality plus. Okay. So what is E infinity? E infinity is defined as, well, not surprisingly, it's a group action. Okay. So what's the group? The group is the free group with two generators. So it's a countable group, and it's given the discrete topology as always. And then once you have the free group with two generators, you let it act on the space of, this, we call it 2 to the F2, but you can view it as different ways. So one way to view it is attaching 0, 1 labels to elements of F2, right? Because that's what this notation is about. But you can also view it as subsets of F2, right? Because anyway, there is a natural shift action of this F2 on 2 to the F2, which is called this is called the Bernoulli shift, because it makes sense for any group. Okay. So if you have a group element, here's an F2 group element, and here is a 2 to the F2 element. What's the result of this action? Well, it is supposed to be a 2 to the F2 element. So when you try to evaluate it as an element H, okay, this is what happens. Okay, so I put the people who are familiar with this type of thing can see that what I'm using over here is the so-called right shift action. And some people are actually more used to the left shift action because then you have to put an inverse over there. So anyway, but this action will give you, I mean, once you have an action, you have an orbital relation. So that orbital constellation is called E infinity. Why is it called E infinity? We'll see a little bit later. Okay. Yes, yes. H is a single element of F2. Right. Right. The X is the element of 2 to the F2, which is in the power set. So G and H are both elements of F2. Yes, right. So then, therefore, you can multiply them together that way. Yes, right. Okay, so once you have an equivalence relation, you can talk about, abstractly, you can talk about the product, the power, infinite power of it. This is just nothing but it happens on the infinite power space, okay? And the two infinite sequences of elements of X, big X, Xn and Yn over here, they are in this new equivalence, equivalent if, coordinate-wise they are equivalent, okay? So what I want to just say is just that if you have if your original equivalence relation is an orbital constellation, then the infinite power of it is also an orbital constellation because you can concoct a group over here, a group action to make it, happen. So this explains sort of, when I put it like these powers over here or these powers over here, they all make sense. Okay, and they all become. As long as the previous one is an orbital constellation, the new power over here is an orbital constellation also. Okay, and so this is E infinity. What about this equality plus? Well, the equality plus is defined by a more general kind of a plus operator. This is we call it the Friedman-Stanley jump because it's the two persons, Friedman and Stanley, who first discovered this and proved the result about it in exactly 1989. Okay, so if you have an equivalence relation E, we can define the jump of E. This is the jump of E. Once again, it is happening on the space of the infinite powers over here. So two sequences of X, elements of X, Xn and Yn, are E plus equivalent if and only if you take this first sequence over here, you look at its E classes, okay? And but then you just get rid of the order, so you just consider the E classes as a set, okay? And then you compare it with the E classes that are given to you by the other sequence. So as long as these two sets are the same, then that's called E plus equivalence. So basically, another way to describe this would be to say that every time you have an xn, you will be able to find something in yn that is equivalent to it, and vice versa. This is the other way as well. So that will be another way to define this, and that's the E plus. And Friedman-Stanley proved that as long as you have a Borel equivalence relation, the jump is always strictly more complex than the original one. So it is a jump, okay? So this, you don't have to read this. I'm just trying to say that if your E was a orbital constellation, then you can verify that the E plus is also an orbital constellation, like over here, okay? So now I have explained everything in this picture over here, and they serve as kind of benchmark equivalence relations for us. And now we're ready to actually go to study, some real classification problems and try to see, maybe, this classification problem has the complexity exactly some of this, okay. But I want to mention that all of this thing I put on the board over here is what we call the pi 03, right? So they're not, in terms of Borel hierarchy, they're not too complex, okay? They're just on the third level, the first three levels. But, and some of them are even F02, so sigma 02, like the LPs, these are sigma 02, like this one over here. But the other ones are pi 03, so they're not too complex. They are all Borel in particular, okay? But we could also talk about non-Borel equivalence relations. So I want to just say a few words about the general theory over here. Just the few facts that I demonstrated on the previous slides took probably 20 years to figure out. So anyway, the first result of the field is to know that all orbital equivalence relations is analytic, and then Silver in 1980, this predates the entire theory. He proved that, this is called a Silver dichotomy now, he proved that for any co-analytic equivalence relation, E, exactly one of the things happen. One is that either it has only countably many equivalence classes, or else the equality of the reals is broadly reducible to E. In particular, E would have perfectly many or continuum many classes. This looks a very simple result, but it's not easy to prove. Okay, even up to today, I think that so we have to use some sort of method of forcing to prove it, and it's not so what we call the effective for discrete set theory of forcing. Okay. Anyway, this is the first result, and I want to mention that and of course we also know that this is for co-analytic equivalence relations, but for analytic equivalence relations on the analytic side, we also know that the silver dichotomy fails. Okay, because there are a third option over there. Okay. So at this point, I want to mention that this is one of the biggest open problem in the field, which is still open now, which is in the spirit. It's called the topological vault conjecture. It has a long history, as you can see from the dates. But basically what it says is that we know the silver dichotomy holds for co-analytic equivalence relations, and it fails for analytic equivalence relations, but we don't know what happens with all orbit equivalence relations. So for orbit equivalence relations, does the silver dichotomy hold? That's the question of topological vault conjecture. Okay, and it is wide open right now. Okay. Okay, anyway, this is a little bit embarrassing because this would be even kind of, you would consider the very first problem. This is sort of like the continuum hypothesis of this field, right? Because it's either countable or else it's a continuum. So, but unfortunately, we don't have an answer. And it's provable that that result doesn't depend on, for example, things like continuum hypothesis. Okay, so if you have an answer on the continuum hypothesis, you should have an answer outright. Okay, so anyway, now I want to come back and justify this notion of infinity. So what is the infinity about? So this is the nice theorem that the Becker-Keckers proved in 1994. They basically proved that for any given, if you fix your Polish group and consider all of its actions, there is always a most complex action in some sense. Okay, that the action is complex because the orbit constellation it generates is the most complex among the all the other actions that it can generate. Okay, so this is the so-called universal orbit constellation for that group G. Okay, for every group there is such a thing. Okay, that with this result we can actually go and consider the equivalence relations group by group basically. Okay, and also another nice complementary theorem proved by basically based on the old result of Mackey, Greg Force proved it, which is that if you have two groups G and H and G is a closed subgroup of H, meaning that H is bigger, then H is capable of producing more complex equivalence relations. So this is basically saying that if H is bigger, G is smaller, then the universal equivalence relation generated by H is more complex than the universal equivalence relation generated by G. Okay, so this is a nice complementation of the Becker-Keckers result. And then I mentioned Ouspensky's result before, which is that among all the Polish groups, there is the largest one, which is the isometry of the Eurozone space. So meaning that if you put in place this group by this isometry of U, then this guy over here, which they prove exists, is the orbital constellation that is the most complex orbital constellation of all orbital constellations. Okay, so anyway, so there's some nice results in this theory about how to tell apart the complexity, relative complexity of equivalence relations. Okay. So let me just give you a couple of random results over here. For example, based on Grayev's theorem, old theorem, one can show that among all orbital constellations of a billion Polish group actions, there is a universal one. Okay. So what I just said was that among all Polish group actions, there is a universal one. And if you restrict your attention to a billion ones, then there is a universal one. Of course, this is based on the old result of Grayev, which is not very, explicit. So also happens to be in 2003. I have a result of working together with Pestov. We show that if you one of this universal orbital constellation for a billion Polish group actions is realized by just looking at the group L1. The additive group of the Banach space, separable Banach space L1. So that gives you the universal orbital constellation for all billion group actions. Anyway, another class of groups which is very, very important to us is the so-called non-Archimedean Polish groups. Officially, it has a topological definition that there is a neighborhood base of one consisting of Köppen subgroups. That's the non-Archimedean definition. But once again, Becker-Keckers proved this very nice characterization, which says that among Polish groups, non-Archimedean just means that it is a closed subgroup of S infinity. Okay, this one group, S infinity, automatically becomes the universal non-Archimedean Polish group. And also, it is isomorphic, it's the same thing as being the group being the automorphism group of a countable structure. So this is how it is, this whole subject is all of a sudden connected to logic. Because in logic, we study model theory, we study countable structures, and automorphism groups of them. Okay. So this becomes a very, so S infinity becomes a very important object, very important Polish group. And many of the examples I gave, the reason I gave this, E infinity, etc., these examples, E infinity and equality plus, etc., I put them over there in the center because they are all S infinity constellations. I said that, once you have a Borel constellation, you can always consider the jump of it. So you could consider the jump of the jump, like equality plus plus and equality plus plus plus, etc. Okay, all the way up the omega 1 many pluses. Okay, and all of them are actually S infinity orbital constellations. So there are some researchers like Scott and old result and Gregkors and Keckers and Lavaux, they proved that basically every Borel S infinity orbital constellation is Borel reducible to one of these pluses, like the omega 1 many pluses. They form a cofinal class in the Borel constellations that are generated by S infinity actions. Okay, so this is just to give you a sample of kind of theoretical results, which is there's a rich collection of them. Okay, but now. Sorry, I think I need to take maybe the full 58, 59 minutes. So I do want to consider the classification problems in mathematics, right? So how do you classify certain mathematical objects up to certain notion of equivalence? This is very typical in mathematics. For example, classifying manifolds up to homomorphism or diffeomorphism or something like that. So basically what we do is we need to, in order to use this theory, we first need to collect all these mathematical objects and then form a Polish space of them, okay? And then now the notion of equivalence will become an equivalence relation on this Polish space. And then the third step is we try to compare this equivalence relation with the benchmark equivalence relations that we have understood somewhat in the theory. And so that is how we do it. And because of the time, I'm going to skip the next few slides over here, but just to say that I was going to give an example of the isometric classification of compact metric spaces, how to make this all the compact matrix spaces, together as a single polar space. Okay, and I was going to mention two methods. One was given by Vershik, and the other one was given by Gromov. They look very different, but they serve the same purpose. And the Gromov's result was that once you have done that, you can prove that the isometry relation on this compact matrix space is Borel reducible to the equality of reals. So in other words, you can assign a single real number as its complete invariant. Okay. Anyway, I was going to give a proof, and now I'm not. I just want to wrap up my talk by giving a whole bunch of examples of the results of the theory. Like, for example, we have this. I talked about the universal orbit constellation, and here's a whole bunch. Here's a whole bunch of examples that have been studied in this theory. For example, the isometric classification of all Polish metric spaces. This looks like a sort of a continuation of Gromov's study. And then the isometric isomorphism classification of all separable Banach spaces. This looks like a another functional analysis. And all separable C-style algebras up to isomorphism, or all compact metrizable spaces up to homeomorphism. And for example, all continua, second countable connected compact Hausdorff spaces up to homeomorphism, etc. All of these have been shown to have the same complexity, which is happening on the universal level for all orbit constellations. So they're more complex than any Polish group action can give. Okay. So what about S infinity? This is also an important class, and once again there are even more results. My selection over here is kind of heavily biased by my own experience of working with them. So almost sort of all the countable structures you can think of turns out to have this complexity isomorphism relation. Turns out to have this complexity. For example, the countable graphs and countable fields and etc. The Boolean algebras. So I want to point out to the Paolini-Shella result, which is all countable torsion-free abelian groups. It's published in 23, I believe, or maybe even 24 in the Annals of Mathematics. So anyway, some of these are old results, but some of them are very new. Okay. And then what about the E infinity? E infinity, remember, was this very low level kind of complexity, but determining a problem to be of this complexity is not necessarily easy. Not just because the problem is actually happening on a lower complexity level, make it easier to determine its exact complexity. Does that make sense? Okay. So anyway, for example, this E infinity is I probably forgot to put it on. Why is it called E infinity? Because it is a universal equivalence relation among all countable group actions. Okay. So anyway, even if it's only generated by an action of a free group with two generators, it actually can, it surpasses the complexity of all countable group actions. Okay. So anyway, for example, here there are some really interesting ones, like Simon Thomas proved that the isomorphism classification of finitely generated groups, or Clemens proved that the topological conjugacy classification of all Bernoulli subshifts. I mentioned the Bernoulli subshift, okay, and Clemens actually proved that this is actually the conjugacy classification is actually happening on that level. Okay. So I mentioned the three of these, and in fact, you could actually point to any kind of benchmark equivalence relation and say, what are some natural equivalence relations? What are some natural classification problems that are corresponding to this equivalence relation? And many of them do correspond to natural classification problems. And so here are some other examples of kind of miscellaneous examples. So for example, the first one by Burakaya, he considered topological conjugacy classification of all so-called pointed minimal counter systems. So these are minimal counter systems with a point, a specified point. So turns out this equivalence relation is bireducible with this equality plus. So equality plus really corresponds to something, some classification. So this is a familiarity. This is a folklore, right? The unitary equivalence of all unitary operators, for example. Okay, that is given by the spectral theory. So we can actually sort of say that because of that theory, say that this is bireducible with this particular equivalence relation, which we call the measure equivalence. Okay, and then isomorphism classification of countable torsion abelian groups, as opposed to torsion-free, which is just the Paolini-Scheller result was about torsion-free. And this one is torsion. It's bireducible with something, here I say equality on them. This is an equivalence relation that is actually incomparable with, the other, equivalence relation that I mentioned. Okay. And the Lavaux-Rosenthal result, that isomorphism classification of all separable Banach spaces, which is obviously a very important equivalence relation for functional analysis, is bireducible with the most complex analytic equivalence relation. So I didn't mention this in my previous, because it's not an orbit equivalence relation. This is the only example in this talk that is not an orbit equivalence relation. Okay. It's sort of happening on the most complex level among all analytic equivalence relations. So the point of, I'm sorry that this part of my talk is super fast. I just want to give you a sense that that a lot of these natural classification problems have been studied in the theory, and for many of the problems, their exact complexity have been determined. Okay. Of course, there are some even more open problems, because there are actually classification problems for which the exact complexity have not been determined. So I just want to mention some, for example, the isomorphism relation of ergodic measure preserving transformations. This was in some sense already posed by von Neumann in the 1930s. Of course, not in this form. This is still an undetermined equivalence relation. But just to prove that this isomorphism relation is non-Borel, was a paper published in 2012 in the Annals of Mathematics, and by three authors: Matt Foreman, Daniel Rudolph, and Benji Weiss. Okay, so then on the topological side, this was ergodic theory. Basically, some people call this a basic problem of ergodic theory, and then on the topological side, you could the corresponding thing was minimal counter systems, and the topological conjugacy of minimal counter system has not been determined, and the minimal subshifts is known to be simpler than that, but its exact complexity is not determined. Okay, and finally, something that came up more recently, that Kekres, Nies, and Tent wrote a very nice paper recently, and they proposed this new program called, I call it the KNT program, which is anyway, this is my last slide anyway. So, which is to talk about, study the topological isomorphism of all closed subgroups of S infinity, and it's known, they proved that it is an analytic equivalence relation, because it's not obvious that it's an analytic equivalence relation, but it is. They proved that it is, but we now need to find out exactly what its complexity is. Okay. So anyway, and oh, okay, there we go. And with that, I'm ready to finish the talk. Thank you very much.
Okay, so you know that classification problems has been really the challenges in the theoretical community, and I think that their work found a way to classify, to answer why some classification problems are much harder than the others. And I think it's a very good way to understand why we are open to that. Thanks. Any questions?
So, going beyond the Braille, but take countable Braille.
Say again?
Take countable selections, but in the context of determinacy.
In the context of determinacy?
Yeah, in other words, so they each have. So if you have two Borel countable equivalence relations, and you ask for reducibility, but you don't say Borel, just a reduction in the AD world, like in L of R, say, is it complete sigma to 1?
So first of all, I don't know the answer.
So are the Borel equivalence relation, countable Borel equivalence relation, where there's a very complicated, like projective reduction, but no analytic reduction or no co-analytic reduction? Can you code effective cardinalities into countable Borel equivalence relations?
Yeah, so I think if you just restrict your attention to countable Borel equivalence relations, then the answer should be yes, because I think, because they are actually very effective objects, because, every countable Borel equivalence relation is given by a Borel action of a countable group. So I think the more tricky sort of question for us is if you bring Borel bireducibility into this and say, let's consider not just the countable Borel equivalence relations, but all equivalence relations that are bireducible or even Borel bireducible with the countable Borel equivalence relations. And then there's something very tricky because there are actually equivalence relations that are reducible to countable Borel equivalence relations, but they are not bireducible with any one of them. So in other words, this is saying that the countable Borel equivalence relations, there are many holes over there, like in terms of the, and that makes it tricky to study. So it's not really it's not closed. It's not closed. It's not downward closed. It's not dense. It's not known to be dense. So this. Yeah, so basically, I mean, if you think about the degree theory, right, in computability theory, there are many actually results. It's incredible that they can prove like a lot of things, like a density, minimal pairs, and this and that. But over here, none of that is known. Okay? So there's no density, there's no minimal pairs and things like that. So the flavor that is being, I digress because this is not really addressing your question. I think I never studied that in the AD contest, so I don't know the answer. But right, yeah, But in general, like. So this is the reason why the theory over here takes the form that is, instead of trying to construct artificial equivalence relations, we tend to focus more on the equivalence relations that come from the kind of a natural context. Yeah.
Okay, there's some more from the online question.
Oh, I see. So what is it? Oh, okay. These theta appearing in the reduction, are they typically not computable? Sometimes they are, but the majority of the times they're not, right? Because these are Borel, so depending on what you mean by computable, right? Because there's a effective descriptive set theory, basically saying that if any Borel map can be viewed as an effective Borel map with a parameter, with a real parameter. So this majority of these things, they are not like outright computable or light phase, but they are, if they're Borel, they are kind of, at least in the sense of higher recursion theory, they are computable with a parameter. Yeah. And
okay, any other questions?
yes.
Thanks for the talk. So I want to ask, Borel bireducibility is an equivalence relation itself.
That's right.
Right.
Exactly.
So can I somehow make it Borel? Like I have a Polish space of all equivalence, all Borel equivalence relations.
Yeah, that's a great question. It is not Borel. It is it is at least on the sim 1-2 level, and we already, like, there are some results which shows that it is yeah, I mean, I think there are some results which shows that they are at least pi 1 hard, or maybe even sigma 1-2 hard. Yeah.
I see. Okay, thank you.
Okay.
Okay, so let's thank our speaker again.
Okay, thank you.
Wonderful talk.
Thanks.